Okay, then based on the measurable function and the measure space, we can define integral on a measure space and a Lebesgue space. That is a different, clearly different between Riemannian Riemannian integral. So, first we can define a simple function. A simple function, as you see, that is like a step function. Okay, but that is okay. Some part of the simple function is like a step function, but step function is all domain which consists of this part is interval. But a simple function, the domain need not to be interval. As you see, the definition of interval that allows this part. But note that if we consider, for example, that or that example, that is not interval. That is, of course, that is also not interval. We can say, everybody says this guys is not interval. That is not interval. That is also not interval. Okay. Only this part is open interval. Okay. As you say, anyway, as you see, the step function allows every subset, even a measurable set. Okay. That is main difference between a simple function. Simple function allows only interval. Step function, simple function allows this part that is not interval. So, based on this, we can define a integral based on simple function if a canonical representation psi is given. And if we define this, then we can check that the general property of integral satisfies. And as I said, the Lebesgue integral, we can define, based on the definition, we can define Lebesgue integral. That is, does not different Riemannian integral. For example, if we consider domain is given, okay, like this, if we consider the area of this, okay, blue part, if we compute the area, then in Riemannian sense does not integrable. However, in Lebesgue sense, that is integrable. Okay, as I said, I cannot deal with everything of the measure theory in one lecture. But note that we can anyway a measurable set. We can construct a measure space, and based on a measure space and mu star measurable function, we can define integral by defining a simple function. And if we define this integral, that satisfies the general property which in Riemannian sense holds. Okay. Then let's see another topic of the Mendel theory, Radon-Nikodym theorism. This theorism is important in probability theory. Because in probability theory we can define a measure, because we can construct probability measure that is a measure, and we can define a similar way we can define probability density function, which is like this. Okay. Anyway, that is very applicable in probability theory, because that suggests the expectation estimate on expectation of conditional probability. Okay, this is important part of the Radon-Nikodym theorism. And if we in we can define a generalized Kullback divergence distance. I will use this concept. So, okay, let's go definition 6.13. We can define a sigma finite if it's measure space given is a sigma finite if X is the union of countable collection of a measurable set, and each of which has a finite measure. Explicitly, that is finite, then X is construct the union of measurable set. Note that a remarkable point is that the definition of the sigma finite is not unique. There are many following many definition of the so-called TFE, take-off following equivalence. If we search the Wikipedia, there are several equivalence definition of the sigma finite. So that is one of them. And if we consider two measure sigma, mu, and nu, then we call nu is absolutely continuous if for any measurable set mu satisfies this condition, then nu also satisfies zero measure, which is denoted by denotation is written. If this absolutely continuous satisfies, then we can denote it by this situation like this. Example, as you see, is a measurable space, and suppose F is a non-negative, and define the measure nu is defined by like this. Then we can check that this condition. So the radon-Nikodym theorem is described by let mu and nu be sigma finite measures defined on measurable space. Important point is that that condition is important. Without this condition, the statement fails. And suppose absolute continuous condition, then there exists unique non-negative measurable function such that satisfies. Okay. That is a radon-Nikodym theorem. That is called some others that is called fundamental theorem of calculus, because F is written as the mu. If we substitute these guys, then it is written as the mu. Written as like this. Okay. Then based on the construction auto measure, we can define product measures on product space. We can define a product measure space on the given set, product set. But the process is a little complicated, but the idea is auto measure. From auto measure, we can construct a measure, but the object is just changed as a product space. Okay. So as you see, the following proposition, we can construct auto measure. We can construct a product measure. If a measure space is given, and if we define a mu star measurable function, also we can define integral on, that is double integral, or generally multiple integral on a product space. Okay. So in particular, like a traditional double integral, so-called Fubini's theorism, generally Tonelli's theorism, I don't know the spelling, it satisfies. Change. If we change the step integral, ABCD, that is also satisfies. Okay. So Fubini's theorism is also satisfies in specific condition satisfies. Because the double integral is well defined and probability measure, we can apply this situation of the probability measure, so-called probability joint density function. Okay, so if the function is given, as the image is in Wikipedia, we can define a probability density function which is hold is dy dx is equal to 1. And this two part which is called marginal distribution. Okay. Anyway, if we define double integral on a measure space, we can define the probability density function on a probability measure space. Okay. So that is the basic idea of double integral. And now the last concept on the measure theory is about LP space. Let Xm measure space is given and consider be a measure of a function with 1p minus. The case is classified two cases. Okay. So yeah, in that case, if we define fp is defined, that it satisfies the norm condition. In that case, we can define the LPX is collection of the function with FP norm is finite. And if P is infinite, that guys is defined the bounded. If bounded, okay, F is almost everywhere on X. That is almost everywhere, which means that all subset X except measure 0. We does not consider a zero measure set. Okay, in that case, L minus infinite x is like this definition, collection of the measure of a function f infinite norm is finite. Okay, but for technical reason, if we define f and g is defined as for any, regardless p is here, in collection contain including an infinite, then that relation is the equivalence relation. So it's called the norm space LPX quotient is called a LP normed space. In general, because this is equivalent relation, that should be a symbol or bar equivalence, that means, which means that equivalence relation. But that is so very tedious process. Tedious, not so if without no confusion, we denote just f and LPX star quotient space is just LP